Hello. Great. It looks like we're on. Um, Thank you, everyone, for coming back. I appreciate it. Hopefully, you got up to get some leg stretchies, work out those limbs a little bit. Next, we have Kartikeya Sharma. Kartikeya is a senior associate information security engineer at Equinox. He holds degrees in computer science and accounting from Goshen College and a master's in computer science from the University of Oregon. He specializes in using machine learning to combat cyber threats. Please help me welcome Kartikeya.
Hello. Thank you for the introduction. So today I'll be talking about utilizing graph neural network to detect DDoS attacks. So I'll be first introducing a little bit about graph neural networks, what are they, and then I'll be talking a little bit about DDoS attacks, and then how you can build a graph two different ways to perform DDoS detection using graph neural network. So yeah, let's start with what are graph neural networks. So if people are familiar with neural networks, graph neural networks or GNN are kind of trendy topic, not as trendy as LLMs, but they have been in talks a lot recently. So let's just talk about what are they. It's pretty simple. They are a powerful machine learning tool to learn from connected data, which is a graph, and they help us uncover hidden patterns better than the traditional neural networks. So in GNN, nodes represent entities or objects. For example, in case of DDoS or network, it can be an IP address or a traffic flow. And edges represent the relationship between those nodes. So it could be, an edge could be a similarity between two different IP addresses, or one IP address going to a traffic flow, which could be a source IP address, and the other could be a destination IP address. So edges could be made a lot of different ways, whatever you can imagine. So what actually GNN does? A lot of people think it's like a rocket science or something. They are super different from like traditional neural networks. They are not. They're just how you can create embeddings using the nodes alongside or in a node's neighborhood. So basically, they just learn from a connected node to create new embeddings. And once those embeddings are created, they're just passed through a normal neural network layer, whatever it is, linear layer, like 5 linear layers. So that's it. It's not as difficult. I mean, you can create a lot of different methods. I mean, there are a lot of different architectures now, but the core of it is super simple. So I'm hoping to actually show you all a website I created. So hopefully everyone can see that. So this is the website I created where you can see how a GNN works. First, I created a graph. This is a 4-node graph connected with different edges. Every node has a tensor or features, whatever you want to call it. So after that, how the message passing or how the learning happens from different nodes. So every node or neighbor is sending messages to its neighbor. Once the messages are sent, you just do feature aggregation. The simplest way is to add them all, or do a mean, or whatever. Now, a lot of new techniques are doing GRU, which is kind of like a neural network, Right now, we're not even doing any machine learning. We're just creating new features depending on the neighbors of a node. So that's it. That's how simple it is. So going back to the presentation. Oops. Um, so GNN are actually been used in a lot of different domains: social network, knowledge graph completion, recommendation. Like in Amazon, they've been using it a lot of, I think, since the beginning. Pinterest. So yeah, let's just talk a little bit about how they are different than the traditional neural network. So the input structure is a graph, and traditional neural network is like a grid-like input. You know, all the features, thousands, 10,000 different features are not 10,000 different features, 10,000 uh, an array of 10,000 features are sent into a neural network. So relationship, a traditional neural network doesn't really have any relationship between different entities, but GNN has relationship because of edges. There are node level tasks, of course, in traditional neural network, but you can classify node or predict node in GNN. Of course, no edge level task. You cannot do a link prediction or edge classification, but you can do that with a GNN. Graph level tasks, of course, you can classify a graph in GNN, and you can do the same sample level classification in a traditional neural network. This is a big one, permutation invariance, because a graph is permutation invariant by nature, so this helps a lot. But in a traditional GNN, if you actually change the structure of input, the results could change, but that does not happen in GNN. And the last one is interpretability. I mean, of course, both of them are still kind of a black box, but using like which nodes or edges are more influential, you can probably interpret GNN in a better way compared to traditional neural networks. So yeah, let's briefly talk about the milestones. Initial concept emerged in 2005. Then they built spectral approaches. And in 2017, a big thing happened, which is GCN. I think it's probably one of the most cited papers out there in GNNs. And after that, 2018, graph attention networks came in. And after that, they became more scalable, batch processing and stuff. And now they've been used in a lot of different domains. So let's talk about the publication. You can see the publications kind of skyrocketed over the years, exponential progress. Same in the important conferences. There've been a lot of big conferences are publishing a lot of GNN paper now. So yeah, that was a brief introduction to GNN. Let's talk about DDoS attack. So DDoS attack is nothing but an attack to overwhelm a target, a server, website, a firewall, whatever. So we can classify them in 3 different ways. First one is volume-based attacks. The main goal is to saturate a network. I think UDP flood is a big example of that. So normal people or normal requests cannot, cannot connect to that network because it's been saturated. The other one is protocol attack, which is overwhelm a firewall using something like ping of death or other attacks. And the third one is application layer attacks, which a lot of people hear about, which is just attacking a website or any application like database. Like HTTP flood is a big example of that. Just you send like millions of requests per second, so normal users can't connect to it. So yeah, so what are traditional approaches for DDoS detection? I think a big one is filtering technique. So just block the known IP addresses or ports. Statistic analysis is a huge one too. It's kind of like an anomaly detection. If traffic is deviating from norm, just block it. normal traditional machine learning methods like k-nearest neighbors, neural networks, again, pretty traditional ones. So, I mean, there are some good things about traditional approaches. They're simple, and they do not need a lot of computational overhead. I mean, you can actually put them in an edge device, and it'll be much easier than other crazy neural network. They're effective against known attacks. If an attack is known, they'll do good. You can interpret much easier compared to, again, huge neural networks. Um, so, but there are lots of disadvantages. The adaptability is huge. They cannot adapt to new attacks. Hard to model complex relationship, like high false positive rates. Again, difficulty detecting low volume DDoS attacks, which happens a lot. So now let's talk about the GNN approach and how we can represent a network as a graph and detect detect DDoS based on that. So first, how we can represent it as a graph. So a node could be IP address, a port, anything, traffic statistics, and an edge could be made between those nodes depending. For example, you can group similar IP addresses together, or you can group IP source and destination IP addresses together, and you can use different features for each node or edge. For example, bandwidth could be a big one for edge, and you can think about a lot of different features. And once you have a graph, you can easily use a GNN model to classify nodes as malicious, or probably the whole graph as malicious, and detect a DDoS attack. So the good thing about this approach is you can learn the features in an automated way. You can model complex relationship, and it can generalize to unseen data. Disadvantage is complex computationally, and could be hard to interpret too, just like an LLM. So yeah, so now let's just deep dive into two different graphs and how we can detect a DDoS attack based on those graphs. So first, we will build graph where we will use packets as nodes. So over here, the packets are grouped by source and destination IPs. And so whatever packet has the same source and destination IP, they're just grouped together. And they're sorted by timestamp in ascending order. So if a packet is sent first, it'll be first one, and then just like that. Then node creation is pretty easy. Packets are nodes. They're limited by a predefined number. You can define it depending on your use case. A lot of time, this is just passed as a hyperparameter. You can use different features, for example, protocol type. An edge in this situation would be an edge between packets which are going in the same direction at a time. And there could also be an edge between a packet which is going in one direction and the other packet which is coming back probably from source. So yeah, let's see this graph let's visualize it. So over here, the TCP packet is going to destination, then there's TCP packet coming back. Oops, sorry. And there are two different TCP packet then sent to destination, and all these packets are coming back. So you can see there's an edge between packets in two different directions. This is forward direction, and this is backward direction. and there are also an edge between packets in same direction. Oh, you cannot? Oops. Sorry. Yeah, I don't know. Um, but yeah, you can. I was just talking about the first node, which is TCP, going in the forward direction, and the second node, which is going in the backward direction. So there are edges between those nodes, and the nodes which are in the same direction, for example, forward, all those packets have edges between them too. So yeah, it's a pretty simple graph. I can answer questions based on that later. Um, so I do not want to go pretty deep into the GNN models over here and make it too complex. But this is a graph classification problem because you are creating small graphs, small packet graphs. So um, in this situation, we are using GIN, which is graph isomorphism networks based on graph isomorphism concept. And we are learning the embeddings based on that. And once we learn the node embeddings, it's just become a normal classification problem where you pass those embeddings through a linear layer and maybe use a softmax after that, depending on your problem, um, and just classify an attack as DDoS or not DDoS. So over here, this was from a paper where they used a similar approach, and they used it on 2 different open source data sets, and the accuracy was pretty high. I mean, for the CIC IDS 2017, the accuracy was extremely high. For DOS 2017, the accuracy was around 9751, which is not that bad. The good thing was the F1 score over here was pretty high for the first one, and was not bad for the second data set. F1 score would be the most important in predicting or classifying a DDoS attack. Yeah, so that was the first graph creation, and let's talk about how we can create a second kind of graph. So over here, we will use traffic flows as nodes. This graph is super simple. We have 2 different kind of nodes over here. One is host nodes, which is an IP address. The second is flow nodes, which is just a traffic flow. So over here, we will have an edge between a source IP and a flow based on that node, and that's the same flow has an edge with a destination IP. Very, very simple graph. I'll show you the picture or visualization in the next slide. The features in this situation were 80 features extracted from that flow, like packet sizes, duration of flow, etc., etc. And host nodes, because they were IP addresses, you do not want to put the IP address over there because then it could be pretty bad for the model. So you just initialize it with all ones. Yeah, and edge types, I already described that. Edge types over here, there's 2 different ones: source to flow edges and flow to destination edges. So the thing over here is it's a heterogeneous graph. The other graph was homogeneous. That graph only had 1 kind of node and 1 kind of edges. This has 2 different kind of nodes and 2 different kind of edges. So this is how this graph is. You can see a host attached to or has edges with a flow, and the flow has edge with a different host, which probably be a destination host. So you can just see this graph over here visually. It's a pretty straightforward graph. So just to go on the next slide and talk about how the predictions or classifications has been made over here. I do not want to go in deep technical hole with the, with the GNN model over here, but they used 4 different aggregation functions for 4 different kind of heterogeneous things over here. So first, the message, when the message is passed between a flow node and destination node, they used a different function, and when the message is passed between a flow node and the source node, they used a different function. And when a message was aggregated in a flow node, again, they used a different function. And when a message was aggregated in a host node, they used a different function. So they used 4 different functions over here, just trying to make it as simple as possible. But just to be a little bit more technical, they used GRU over here, GRU, so which is again a neural network. So they made it a little bit more complex than just simple mean, max, or sum aggregation, like I showed you in the website. Again, once they get all the embeddings for each node, it became a very, very simple classification problem. You get all those embedding and pass it through a fully connected layer. Like you can use 3 layers, 5 layers, depending on your use case or hyperparameter tuning. And once they do it, then you can pass it to, again, ReLU or sigmoid or whatever activation function you want to use, depending, again, on your use case. And once they pass it through that activation function, they can classify or predict it as a DDoS or a benign attack. And again, this result is from a different paper where they used the approach I showed you in the last slide, and they actually classified, I think, 5 different kind of attacks over here, and their performance was pretty good. The accuracy was over 99% in every case, but they did not actually they did not say anything about the FN score, which is kind of a red flag because you really need a good FN score in predicting DDoS attacks, because you do not want high false positive or things like that. That will just put the security analyst in a pedestal, so you don't want to do that. Yeah, these are references. If you want to look at them, to the 2 different papers, and that's it. I can open up for questions now if people have questions, and I'm pretty happy to answer those.
Hi. I understand that your focus is on DDoS attacks. What other use cases can you attribute this process to? It seems like you could actually get a lot of different readings based on this process for a lot of different things. I was wondering if you might have had any other use cases you could use this procedure for.
By the process or procedures, you mean graph neural networks? Okay. Yeah, I'm really confused about the question. I don't know. I mean, if you mean graph neural networks, of course, you can use it to a whole lot of different security cases. For example, insider threat detection is a pretty big one. So DDoS is a big one. Whatever you can create a graph out of it, like you can use a GNN. And a lot of big tech companies been using it for a long time. Facebook uses it. I mean, Meta now uses all the time. Google uses all the time. Amazon, Twitter, you name it. So, yeah.
A slightly more technical question. So when you were talking about these nodes pass messages to each other, is that similar in process to MPI in parallel networking or parallel processing?
Not really. I mean, you can make it parallel for sure because depending about the overlap though, but it is an iterative process. So it's pretty easy. You go at one node, look at all the neighbors of that node, get all the messages from that node. You have all the messages and aggregate them or update the node. So I don't think it is like that, but maybe you can make it parallel depending if you do not have a lot of overlapping neighbors. I'm sure you can make it parallel. I mean, there is distributed processing for GNN. Look at DGL library; they do it there. So yeah.
So I'm assuming there's no general case way to parallelize that. So that does lead into another question, which is, what's the latency on this? Because I noticed that one of the data sets that was referenced was for intrusion detection. Is this something that could, in theory, be run in real time on a firewall? Or like, what's the compute and the latency on that?
Yeah, quick answer, no, not right now. It's going to be very, very slow. That's why you see a lot of firewall companies like Akamai, Palo Alto, they've still been using traditional methods. But what you can use it for is actually just use it after you have all the traffic, in your database or something, just to detect maybe like low volume DDoS attacks or just to tune your attack. Like what do you call those things? Tune your filtering techniques based on the detection.
So it wouldn't necessarily be useful for real time, but it would be more useful for sort of a retrospective or for analyzing previous attacks.
Exactly. I think right now it's more useful for analysis, but hopefully in the future, because if you want to detect DDoS in real time, you gotta do it in less than seconds, So it'll be very, very tough right now, but hopefully in future we can do it. So.
I was just curious if there are any out-of-the-box GNNs to tinker with that you might recommend.
Yeah, depending what you're trying to do. For graph classification, look at graph isomorphism network. Hopefully I'm saying it right. GCN is a big one, graph convolutional network. Graph attention network is a pretty big one. And graph UNets, that's my personal favorite. So,
Thanks.
Yeah.